So good morning and good afternoon to everyone. We are in the quantum engineering panel, and we have four distinguished speakers for you. Unfortunately, time is going to be very limited. So I want to let you know that if you do not have time to ask your questions during this session, there will be an open discussion session. And the speakers graciously agreed to be also available during that session. So to start the session at this time, I would like to introduce our first speaker. The first speaker, actually, it's going to be Dr. Joe Barden. Professor Barden in 2009, and he joined the Department of Electrical and Computer Engineering at the University of Massachusetts in Amherst in 2010, where he is full professor. His research focuses on low noise, cryogenic integrated electronics for radio astronomy, quantum computing, and quantum optics. Since 2017, he has also been with the Google Quantum AI team, where he currently leads efforts on integrated circuits for quantum computing. He's the recipient of numerous awards, including the DARPA Young Faculty Award, the NSF Career Award, the ONR Young Investigator Program Award, and an IEEE MTT Outstanding Young Engineering Award. So Joe, the floor is yours.
Okay, let me try and share my screen here. I think this is the right one. Okay.
Good.
All right, I'm still waiting to see it here. Okay, there it goes. So I've been tasked with discussing quantum computing. I'm going to give a quick overview of where the state of the art is today, and then how I see ECE departments as contributing. So I was asked to focus on hardware side. So I want to start with looking at what today's state of the art looks like. So this is one of Google's state-of-the-art quantum computers. It's a 50 qubit, actually 53 qubit device. You see this chandelier-like thing hanging from the ceiling is the dilution refrigerator. This is used to cool the quantum processor to a temperature of 10 millikelvin. Each of these plates is a different temperature stage of the dilution refrigerator, and the lowest temperature is at the bottom here. If you zoom in, you can see the quantum processor is mounted in this package. You have all these high frequency connectors around the output to get signals in and out. If you take the lid off, you see the quantum processor is nothing more than a silicon chip, which has been flipped onto a carrier chip and mounted in a printed circuit board. So the quantum part of the system is just inside of this
Joe,
box.
we're not seeing anything.
Joe, there's issues with your slides. They're not fully shown and they are not advancing.
Let me try removing my external screen.
Yep, there it is.
Okay, now I don't see anything. Okay, hopefully.
We're seeing the dilution refrigerator.
Yeah, let me make it full screen. Okay, so you see it now?
Yep, it's full screen.
Okay. So what I was talking about, dilution refrigerator hanging from the ceiling, and the quantum processor lives on this stage here. If you zoom in, you see there's a package where the quantum processor is mounted. You see a bunch of high frequency coax connectors around the edge. And if you take the lid off this package, you see the quantum processor itself is just a silicon chip, which is mounted into a package. There's another interposer board and then wire bonded out to a printed circuit board carrier. So as I was saying, the quantum part of the system is just this chip. Everything around it is classical electrical engineering stuff. So you have in the back racks of equipment. These are used to generate signals to control the state of the quantum processor. And you see all this high frequency wiring getting down into the system, and then a bunch of microwave electronics on the mixed plate at 10 millikelvin. So this is a pretty sophisticated system, a lot of complexity to get to 50 qubits. If you thought about, like, you know, a DRAM chip with millions or billions of bits, there's really a different scale here. Just to get to 50 qubits, you need all this complexity. So the question is, you know, what can you do with a system like this? And in 2019, the Google team showed that with a system like this, you can actually do something that is beyond the scale of what you can do with a classical computer. So when this was published back then, that was a big deal, because there had been articles saying, for instance, things like you could never carry out computations like this because you have to control too many analog variables and things like that. And this paper, beyond just showing that you could do a computation that can't be done on a classical computer, also helped to validate things like the noise models that people have been using, where you can treat noise as discrete events. So, you know, after this kind of, today people are trying to move towards bigger systems. The reason for that is, you know, 50 qubits or maybe 100 qubits is about as far as you're going to be able to scale these systems due to noise, unless you really reduce the rates of error within the qubits. Today's qubits really don't even meet, at least the superconducting qubits don't meet this 0.1% error rates when you talk about 2 qubit gates. And if you think about it, in quantum computing, what you're doing is you're applying a series of operations on your qubits. So you apply single qubit gates, 2 qubit gates, and run a cascade of operations, and each operation has independent errors. They all add up. So your probability of having the correct computation gets really bad in the end if your error rates are high. So even with 0.1% error rates. Sorry, did someone ask a question?
We're not advancing. We're still just looking at the original deal fridge.
Okay, maybe I won't present.
Yeah, if you just kind of show them in non-presenter mode, so people.
Okay. So can you see it now?
Nope, just a beautiful deal fridge, lots of blue and copper.
Let me try stopping the screen share and starting again.
Everyone loves Zoom.
Yeah, and now I have to figure out which one this is. There it is. Okay, now can you see this plot?
See the 0.1% error rates, blah, blah, blah.
Yes. Okay, so if you look in the bottom right, this is a picture from that paper, and you can see when a computation was carried out with 50 qubits at a depth of 20. So that's 20 single qubit gate operations per qubit and 22 qubit gate operations. You just have 0.2% chance of getting the right answer. That's okay for this, where you could run millions and millions of runs, but if you try and do something, say with 100 qubits at these error rates, you're not going to be able to get the right answer. You know, where the field is moving right now is to develop error correction techniques, or demonstrate error correction techniques to overcome this problem. So did this advance?
Could you go to full screen mode, please? It's some of the stuff is not legible.
Okay, I'm worried it won't advance, but I'll.
Yeah, thank you.
Can you see slide changes now?
Yeah, now it's better.
Okay, so the bottom line I'm trying to get towards is that there's an effort, or roadmaps have been demonstrated to get towards million qubit scale systems. And this is kind of a grand challenge. You can see the 50 qubit system fills a room. How are we going to get to million qubits? And that's where a lot of research needs to be carried out. And so, you know, I would say that it's probably not going to be a million qubit system, probably won't be built at a university, but the research required to get there, a lot of that can be done at universities. So just to emphasize, there are several groups, Google, IBM, and researchers in China, who've all said they're going to get to 1 million qubits in the next decade. So there's this real race going on. Of course, there are a lot of challenges getting there, And of course, that's where academics comes in. So where do the ECE departments fit in? This is a non-comprehensive list of things that I could think of. First of all, there are many different horses in the race right now as far as the technology just to make the quantum processor. And there have been basic proof of concepts of many of these, but there's a lot of engineering still needed. For instance, materials research to reduce defect density and things like that. And some of these devices will really help. In addition, developing new qubit technologies such as, there have been so-called 0-pi and things like that that have been envisioned in the last couple of years, and going and demonstrating these kind of more immune to noise technologies will be important and is an important research area. Also, hybrid systems such as, coupling single microwave modes to optical modes and things like that will be important for future quantum computing. In addition, there's been a lot of work recently on control systems. If you go to, say, the solid state circuits conference, you'll see every year now there are many papers on integrated circuits for quantum control. But there's still a wide array of functionality that's completely untapped. For instance, to the best of my knowledge, there's only one paper on integrated circuits for trapped ion systems. And so there's, as people go to integrate these things more densely, there's going to need to be a lot of work on creating ICs for that. In addition, you need to do the system packaging, optimize the interconnects, and power and so forth. A little bit less at the hardware level, although architecture does have hardware, is that the architecture and error correction, applying electrical engineering techniques to error correction could improve the state of the art. So there's a lot of room for improvement, and actually a lot of research going on in electrical engineering departments in these areas. Perhaps most importantly, at least personally, it took me a long time to come up to speed with this as someone with an electrical engineering background, but not necessarily a quantum background. And so I think that to create the workforce required for future quantum computing development, there's going to need to be programs that teach people both about computer engineering and electrical engineering concepts, but also include enough physics and linear algebra to be able to understand what's going on in quantum computing. So I think there's a lot of opportunities to create kind of focused programs and take advantage of things like the quantum computers that have become available to use through Python packages and so forth. In addition, there's an opportunity, you hear a lot about in the news about quantum computing, and usually the way it's described is computations in parallel and so forth, and that's not really correct. So I think there's a big opportunity to try and explain quantum computing in a more rigorous manner, or not rigorous, but more technically correct manner to the public without requiring so much math. A big challenge, though, in trying to bring people up to speed with quantum computing is that the devices are not necessarily available, and there's a lot of infrastructure required, for instance, to test a superconducting qubit. So if you have a class where you're, say, fabricating transistors, you can just go in the clean room, make a transistor, and measure it on a semiconductor parameter analyzer. Doing that with, say, a transmon qubit is not very easy. And so there's a gap between the kind of paper studies of qubits and their physical realization and all the challenges that come with that. All right, so that's all I have. I'd be happy to take questions when the time comes.
Thank you very much. Do we have a couple of questions? And you can also ask questions on the chat. And like I said, if those are not answered, we'll also have time in the open discussion. Any question from the audience? Just unmute yourself and ask. So I will ask a quick question, Joe, and maybe we can move to the next one after that. Is as you mentioned, the challenge for people who are interested in quantum computing is if you don't have the hardware, how do you get into research on quantum computing? So do you have any words? I mean, you mentioned working with Google. I believe there is ways to at least access to the cloud other quantum computers. That might be one way. Do you have any other?
Yeah, so there's, I think it's really multidisciplinary research. And so the different avenues in are, if there are people at a university already working on quantum computing, collaborating in something that benefits their research. There's, all sorts of avenues in. There's also, as Dominique mentioned, there's various avenues to use small quantum computers through the cloud nowadays. That's really useful for understanding the basics, running small algorithms, things like that. And I think that depending on which mode you're using, which type of qubits, the cost barrier to getting into just directly fabricating them may be too high. But again, collaborating with people either inside of the university or outside. But I guess the first step is really learning the details that you would need to have the conversation with a collaborator.
Wonderful, thanks, Joe. And we may need to move to the next one in view of time, so please stick around, ask questions on the chat. I see some people are already doing that, and you may be able to get some answers there. We'll move to the next speaker, Dr. Celia Mersbacher, who is the Executive Director of the Quantum Economic Development Consortium, or QEDC. QEDC is supported by the government and more than 150 industries, academic, and other members. Previously, Dr. Mersbacher was VP at the Semiconductor Research Corporation, a consortium of the semiconductor industry, and prior to that, Assistant Director for Technology R&D in the White House Office of Science and Technology Policy. So Celia, the floor is yours.
Thank you, Dominique. And I will share my screen. Visible to you all?
Good. Yes.
Great. So thank you very much for the opportunity to be here this year. I think this was one of those events that got affected by COVID early on. And so it's delightful to see everyone and have the chance to talk with you. I am going to kind of very quickly give you a snapshot of QEDC. And then I was asked to speak briefly about quantum engineering research needs from the industry perspective. So I'll touch on some of those, and Joe gave some examples from his perspective affiliated with Google. And so I'll add to what he said and leave you with sort of a list, a little bit of a laundry list. I might actually come back and also, if I have time, answer or speak to the question that came up about researcher access to quantum computing capabilities. So here is QEDC at a glance. The mission is to enable and grow the quantum ecosystem, or the U.S. industry. We are supported in part by the U.S. government with the objective of growing the emerging quantum industry here in the U.S., but there's recognition that this is really happening around the world, and so it will involve supply chains and others outside the U.S. as well. We have a number of objectives, and the QEDC was called for by the National Quantum Initiative Act that was passed in 2018. And so if you look there, it gives some of our charter, essentially. We're to really identify the research that's needed to enable the quantum industry and identify gaps and come up with strategies for addressing those gaps. And we're focusing on both technology and I guess what I would say is non-technological gaps, such as metrics and benchmarks and workforce issues. We have, as Dominique mentioned in the intro, a very sort of broad cross-section of members, small companies, large companies, companies working in quantum computing, communications, component suppliers like laser and cryogenic equipment suppliers, academics. We have about 35 universities that are participating to date, but we have over 100 companies. So we're really sort of at the core is this industry perspective. We're driven by what industry needs, but it will involve academia especially at this stage when things are still relatively early in the development. We do fund research, but we're not a big funding organization. Hopefully over time that may grow, but once we identify a gap, we are able to work with partners, both from our corporate members and from government agencies, to sponsor research to fill some of those gaps, especially in their sort of prototyping stage work. And we require in general that those teams are led by a corporate partner, but they can include academic partners as part of the team. As I mentioned, we have workforce activities going on. We connect students with our industry members. We have a number of efforts that are getting underway to try to make those connections happen and provide students with exposure and opportunities in the industry. We are supported by NIST. NIST selected SRI International, the organization that I work for, to manage the QEDC back in 2018. So I'll speak now, I'll touch on a couple of these enabling technology research areas that we've identified and focused on through having kind of invitation-only type workshops, really deep dives on what the industry needs. And actually, Joe was at the workshop we held on cryogenic technologies and the needs for applications in quantum. This picture is one that you're probably familiar with. It's the sort of super fridge that IBM is building. So to scale up, they have to scale up the cryo capability, and this massive, large dilution refrigerator is where they are now. And that works to a point, but may not scale ultimately to what will be needed, or there is going to be cooling power and other advances that are necessary to keep that scaling working. On the other hand, trapped ions, such as being developed by IonQ, maybe don't require the same level of cryogenics, but they're planning, they want to have things that are sort of rack mounted. And obviously this IBM system is not that. So everything really works better when it's cool in the quantum world. And so even IonQ and people who are working on approaches that don't require the same level of cooling power are looking probably for some cooling capabilities. So what the cryo requirements are from industry's point of view really depends on the application. So we have large volume and large cooling power requirements in some instances. In others, there's really a need for something that's much more compact than is available today. And so those are different sort of avenues for research, somewhat orthogonal. There are many quantum applications where you would like with the quantum to be what they think of as invisible. The cryo community wants it so that when you're designing a system and somebody says, well, we're going to have some cryogenics to cool this down, people don't throw up their hands and say, well, forget about it, that's not going to work. It just should be something that is easy to engineer into your application. For researchers, sometimes it's a throughput issue. Not having to wait over the weekend to change a sample and get more measurements would be a huge accelerator for being able to do research, for example. So having quicker cool down times and more rapid sample changing capabilities. Some standardization would be helpful in being able to compare results and do experiments perhaps across systems. Better environmental control, not just keeping things cold, but vibration and other sources of noise are a problem for many applications. And then ultimately, of course, on the industry side, you want something that's going to be easy to maintain, reliable, something a technician can operate. So the stuff at the top, I would say, is more perhaps academic research areas, and the stuff at the bottom is more where industry needs to kind of step in and do some engineering work. Another enabling technology that's really critical to a lot of applications in quantum computing, but also in sensing and communications and almost everywhere is lasers. Essentially, many quantum systems are at the heart light interacting with some matter, some physical system. And so all of the examples that are shown here depend on having lasers in some shape or form. So whether it's the sort of photonic-based quantum computers or trapped ions and laser-cooled systems, atomic clocks and various other sensing type applications, and so on. You can sort of see the whole panoply here, and really none of these would work without lasers. So the enabling technologies, we did have a workshop on lasers. It turns out that there are people in this area who kind of keep lists and have more than 100 different laser wavelengths and characteristics that have been researched for various quantum applications. And the laser manufacturers sort of scratch their heads and wonder which are the ones that are going to be a big market ultimately, and where should the industry be focused. So on the research side, you're doing a great job of coming up with good ideas. The question is, are all the components there? So this is just an example from the laser workshop that we held. And you kind of maybe can ignore the stuff in the middle that's talking about the energy levels. But over here on the left, so this is for cesium atom-based systems. In order to control the qubit, you need 6 different wavelengths, and those are shown over on the right. Different wavelengths, sometimes combined, sometimes separately, to move between these energy levels. That requires 12 different lasers, because the lasers for the exact wavelengths may not be available. And so there's a lot of photonics and optics, in addition to the lasers, that is required in order to control this system and to make it useful. So, you end up with something that looks like this in the laboratory. And maybe that's fine for researchers, but this is really not a practical application. And so what you really want is something like what's shown on the right. This is the result of the CSAC project that DARPA ran, the chip scale atomic clock. So the picture on the left is actually a NIST atomic clock. The one on the right is something that fits in the palm of your hand. Apologies for not having a scale, but it's sort of, a couple inches on the side. It's not as accurate, but it's good enough for many applications. And so I think a takeaway message I want to leave you with here is that lower swap size, weight, and power requirements and cost ultimately are essential for many applications. And so the picture on the left is what a physicist, would think of. The picture on the right is what an engineer thinks of. So I challenge you all to look at a lot of these quantum research areas and ask the question, is it practical yet? And do we need to work on perhaps reducing the size, weight, and power requirements to really make it useful? So here's my wish list, I guess, of research areas that I wanted to leave behind with you. We've been thinking as a sort of collective group at QEDC about what are the enabling technologies that are going to be needed for various quantum applications. I touched briefly on cryogenics and lasers in my presentation. Joe mentioned control electronics. There's a lot of work that needs to be done there, and we're working on a report with some specific research topics for that. Single photon sources and detectors, as I mentioned, light and matter interaction is important, and often you need heralded photons. You need to be able to get photons on demand, one at a time. And so that's a challenge, and it turns out it's very hard to measure them. I mean, you need detectors, but you need to just know that your source is what it says it is. There are packaging needs. We're doing a workshop in the fall on environmental and vacuum packaging specifically for sensors. And then you need to get the light in and out of the package. And so there's need for more development of optics and integrated circuits, photonic integrated circuits. And so a lot of work in the sort of optophotonic space. And at the bottom here, I mentioned a software related challenge. So intermediate representation is sort of the layer between the hardware and the software. And so how do you run all of these algorithms that people are starting to develop on different hardware platforms? And is now the time to even be able to do that? Or should we just kind of work on things individually at this point? So with that, I will close. I did want to go back to the question briefly, if I have a moment, about researcher access to quantum computing and sort of make a pitch for a program that QEDC and its members helped to put together called QUEST, which stands for Quantum User Expansion for Science and Technology, a nice pronounceable acronym. And if you Google it, you can find legislation that was introduced last year. It didn't go forward, but it's being included in some of the S&T bills that are in Congress now. And it's intended to use some of the NQI funds in NIST or NSF or DOE. I think DOE will end up being perhaps the owner of this program, but it's to be funding that's available for researchers to access, to pay for access and use and time on quantum computers that are available today. So as the quantum computers become more powerful, the research that you could do on them obviously will also grow. And so it's aimed at really kind of creating and supporting the research use of quantum computers, and thereby increase the early market in some ways, but also support a broader research access to quantum computers. So if you're interested in more about that, I'm happy to answer or talk to you offline, but I would encourage you also to support that piece of legislation, because hearing from the universities is always important when something is being considered by Congress. So thank you.
Okay, thank you very much, Celia. Any quick question? Please unmute yourself.
And QEDC, of course, welcomes academic members if you're interested in knowing more about the benefits of getting involved with QEDC. Just let me know as well.
Great. I was going to ask that question, Celia. If anyone is interested, the best way is to contact you directly.
Yeah, I'll put my
academia.
email in the chat. I think you've got it, but I'll go ahead and chat it to everyone.
Wonderful. Okay, thank you. Well, in view of time, unfortunately, I'm sure we'll have a lot more questions as we go. The next speaker is Professor Walsworth. Professor Ronald Walsworth is the founding director of the Quantum Technology Center and Minta Martin Professor of Electrical and Computer Engineering at the University of Maryland. His research interest is in developing precision measurement tools and applying them to diverse problems. He's the recipient of the Francis Pipkin Award in Precision Measurement from the American Physical Society, the Smithsonian Institution Exceptional Service Award, the Duke University Faculty Scholar Award. He's a fellow of the American Physical Society and serves as a distinguished traveling lecturer for the Division of Laser Science of the American Physical Society. Ron, the floor is yours.
Thank you. It's great to be here. I'll try to share my screen. See if this works. Can people see the slides?
Yes.
Okay, wonderful. Hopefully you'll see some resonance, pun perhaps intended, with what you heard from Joe and Celia, and but with more of a focus on quantum sensing. As we all know, there's a lot of investment going on in quantum technologies, most prominently quantum computing, but other areas as well. Big tech companies, governments around the world, and a lot of interest in the United States as well. This is a report called Quantum Frontiers from last fall from OSTP, in which they called out explicitly the need to build the discipline of quantum engineering. And they had 4 primary points. 1, the need to integrate quantum hardware, software, and support technology. 2, the need to establish system-level architecture, abstraction, and testing. 3, enabling modular systems. And 4, work with experts across many different areas to figure out what the new applications will be. Obviously, I think there is a key role for universities in all of these. And then training, of course, the people who will do much of that work. And then, of course, what is quantum technology? It's the application of quantum behavior to practical applications. There are a variety of different quantum phenomena listed on the left here. I won't go through them all. And a wide variety of quantum technologies, which require engineering. My own sense is that from the easiest to realize and the earliest to be realized to the hardest and the one that'll take the longest time is shown on this spectrum that I show here, with perhaps quantum sensing and imaging measurement tools being the earliest to find practical applications. In the 20th century, of course, there was quantum technology too. You might call it quantum tech 1.0. It typically involved the ensemble behavior of many particles of light, atoms, electrons, etc. And here are some of the highlights of the technologies that were developed during that period, of course, to great societal impact across many fields. Much of this was pioneered in the US, and the engineering practices, though still evolving, very important, are now well established in departments at universities. Now we're in the 21st century and we have a kind of new revolution, quantum tech 2.0, where I have the ability to control individual particles or qubits, initialize them, control them coherently, bring multiple qubits together and control their interactions. So we can do things like measure an image at the individual single atom level, or engineer and control matter at the single molecule level, communicate as safely as possible, allowed by the laws of physics with entangled photons, compute exponentially faster for certain problems by exploiting quantum behavior like superposition and entanglement. And of course, there's a wide array of things happening, particularly in the private sector, most dramatically, but also in academia. I'll highlight, as I'm at the University of Maryland, IonQ, which is planning to go public and become the first publicly traded pure play quantum computing company. It uses, of course, the ion trap platform, though there are multiple quantum computing platforms. Quantum sensing, the area I work in, there are a variety of technologies. Don't have time to go through them all. I'll just highlight one, the one I'm involved with, which is using defects, atomic scale defects, quantum defects in diamond, like the nitrogen vacancy color center. There are multiple types of defects, which turn out to be optically addressable sensors of things like electromagnetic fields, temperature, and forces, with good precision, good sensitivity, but also very high spatial resolution. And they can go into a wider range, because the materials are robust, a wide range of environments. In some ways, these sensors provide the best of both worlds, or close to it. Atomic-like behavior, but inside a robust solid-state host that can be used for many things. Over the last decade, there have been a wide array of academic instruments developed, which have been used in many different areas of science. Things like mapping the viscous electron flow in graphene, understanding the behavior of magnetic multi-layer materials relevant to spintronics, biological applications like doing wide field imaging of magnetic imaging of individual living cells and seeing how they behave and grow, and kind of counterintuitive things that maybe wouldn't have thought of at the beginning of the field, but turns out to be very impactful, like understanding ancient magnetism, micron scale magnetism inside of very ancient rocks that can be more than 4 billion years old and can tell us things like the history of the Earth's geodynamo, or if you're looking at meteorites, things about the formation of the planets in our solar system. There's commercialization going on in the quantum sensing field too, across many platforms. Again, in Diamond, there are a variety of startup companies and big companies involved in developing commercial devices, which are beginning to have applications or have a pathway towards applications in a wide variety of areas, some of them shown here, like doing NMR and MRI of individual cells and ultimately proteins, being able to image inside, non-invasively, inside of integrated circuits to be able to see how patterns of currents are flowing, and using machine learning tools to fingerprint activity to see if there are flaws in those circuits. Perhaps Trojans have been inserted. In the longer term, things like autonomous vehicle navigation, having sensors to aid there, exotic applications like mind-machine interfaces, or even helping to enable practical fusion power by having arrays, robust magnetometers that could exist inside the fusion plasma. All these things are being pursued by a variety of, and many more, by a variety of companies that are recently been formed, or large companies. I have a financial conflict of interest in a couple of these companies as a founder of them, which I want to make sure to tell people about. So when we get to quantum engineering, it's an emerging discipline with many challenges. Like what you heard from Celia and Joe, we have to be able to control qubits. We have to make robust qubits. We have to scale them up. There's different types of qubits which are needed for different purposes. Electron spins are great for sensing. Nuclear spins are great for memory. Photons are great for communication, etc. And we have to develop the applications and integrate everything together. To date, the qubit control and robustness have been good enough for research, but not really robust devices. That's beginning. So we have to engineer quantum materials in particular and processes better. To scale up, we have to deal with the problem of quantum decoherence as you get more qubits, and we have to engineer probably things in components or modules, as you heard about before. There's a complexity associated with the diversity of qubits, and so we have to be able to engineer quantum interconnects between those different types of qubits. That's a challenge. And the accessibility of qubits and identifying the high impact applications means you have a demand to be able to engineer quantum systems at a systems level. So systems engineering for quantum technologies, and also train the application engineers. Now, in some ways, this is an old story, right? There were new fields that emerged in the past that were not once disciplines in engineering, but within the last, say, 70 years or so became disciplines in engineering. And perhaps this will happen with quantum too. Time will tell. And that's a challenge for us as academics to develop this discipline in an appropriate way, in a kind of smooth way. You can't start departments on day one, but we have to be able to take on that challenge. Now, a couple words about Maryland, UMD. We've long been a leader in quantum science, highly ranked with our institutes there. And we're moving to become also a leader in quantum engineering with the founding of QTC, the Quantum Technology Center, which has its motto to innovate, translate, and educate in quantum technology. The home of the QTC is a new building known as the IDEA Factory, which will be completed very soon. And what we're doing in quantum engineering education at UMD is developing right now a quantum science and engineering cross-disciplinary minor that might evolve into a major or even a department with time, and a professional master's degree program in quantum engineering. I want to end by highlighting something related to previous discussion about how are we going to do this quantum engineering education and do it, in my opinion, with equity. I don't think that there should be winners and losers. That is, a few special universities, because of their large endowments, or that they win big grants, or they have special relationships with companies, get to be able to train leaders in quantum engineering and everybody else doesn't. What I would suggest is, probably with support from the NSF, Dominique, at a national level, that we need to be able to develop probably regional leading centers where state-of-the-art training hardware can be. You can't do everything on the cloud. People are going to need to be trained with hardware. And then those be not just for they'll probably be at leading universities, but they're regional for all the colleges and universities in the area to the degree that they want to participate. For the small colleges, the HBCUs, the state universities, et cetera. You could imagine, for example, Dominique, that the QLCI universities could play that kind of a role. And I'm just making a suggestion here. We need to develop, and it's going to be expensive because the hardware and the instrumentation will be expensive. It needs to be staffed. Similar things happened in the past. For example, when nuclear engineering grew up, there was a way to support the development of training facilities, nuclear reactors, and other Van de Graaff systems, et cetera, at universities. Thank you very much.
Okay, thank you, Ron. Any question from the audience? I think somebody is prompting me to move to the next speaker somehow. Ron, if you can stay around for a little longer.
Sure.
We'll move forward since time is flying by to Maria. And hopefully we'll get the chance to chat some more in the open discussion. So Maria Mikhailova is a senior software engineer in the Microsoft Quantum System team. She drives the developer outreach and education work for Microsoft Quantum Developer Kit, out new efficient ways to help people learn quantum computing. She is the author of the Quantum Katas project, an open source collection of hands-on tutorial and programming exercises, the Q coding contest series, introduction to quantum computing course taught by Microsoft at the University of Washington, and she has taught a course on quantum computing at Northeastern University in Seattle. So Maria, the floor is yours.
Thank you for the introduction, Dominique. Hello, everybody, and thank you for inviting me to speak here. Let's see if you can see my slides.
Yes.
Okay, good. And we will see whether I can actually switch between the slides in just a second. So today I'm going to try and round up a little the presentations of other great panelists, talking a bit about the quantum computing education from a quantum software point of view. As we all know, quantum computing is going to be a full stack effort, from building commercial quantum devices, controlling them, basically all the components you have heard about already. But on the top layers of the stack, we are going to have a specialized software that helps software developers write programs for quantum computer and does all kinds of clever things in error correction and layout and other specialized things. And we found that often starting quantum computing education with quantum software level makes it more accessible for folks who don't have a solid physics background, as is the case for a lot of students, especially undergraduate students. But first, let me share a little bit of data on the demand for the quantum jobs, because this is one of the first things that students are going to ask if you're going to offer a quantum computing class. What are my perspectives after I take this class? What kind of jobs are going to be open for me? How big is the market? How big it's going to be? Well, 15 years ago, when I first heard about quantum computing, it never occurred to me that it can be a career, especially that it can be a career for me. And yet here I am. So the field has grown in that time. It actually has grown quite considerably just in the past 4 years when I joined Microsoft Quantum team. I borrowed some data from a survey paper that you can see here on the screen, and it indicates that the amount of industry quantum jobs, not just research, specifically industry, has grown fivefold since 2016 to 2019. And there are several hundreds of job openings worldwide in the industry, which combines several kinds of companies in three main categories: big companies that have significant quantum computing investment, but also significant investments in other directions, such as Microsoft, IBM, Google, Amazon, Honeywell. Well, now that Honeywell is spinning off their quantum computing division into a separate company, this may or may not be true any longer. Second, smaller companies and startups that specialize specifically in quantum computing, different aspects of hardware, software, or education. And finally, there are companies that are starting to experiment with quantum computing to see whether it fits their needs, whether it can solve the problems that they have, such as optimization problems, chemistry problems, that kind of things. And we expect that the market for quantum computing jobs, quantum engineering jobs, is going to grow. In fact, you have seen a similar slide in one of the previous presentations, but governments worldwide are starting to recognize the needs to advance quantum computing, both in terms of advancing the research, but at the same time accelerating education, making sure that we have an quantum-ready workforce. Let's take a quick look at what kind of education universities can offer in quantum computing. Okay. So the most typical and historically dominant kind of education is graduate level programs in quantum computing. They are usually offered by universities and joint centers with very mature, established researcher base, because they offer multiple courses on different aspects of quantum computing, basically on all layers of the stack, from physics to information processing to software. The specific set of courses can vary, of course, from university to university. Here is an example of courses from University of Waterloo graduate program. You can see that there are plenty of courses there. Lots of stuff to learn. But the challenge with graduate level programs is that they are very heavyweight, and if they're only offered by a limited pool of universities, basically a university needs to build up this research base, this variety of researchers working on different aspects of quantum computing before they can start to offer this kind of program. So it's not going to be very broadly accessible. Another kind of more democratic layer, I guess, are undergraduate level courses. Usually these are kind of standalone courses, not a whole specialization. They're usually electives, so folks can choose to do or not to do them. And they can be offered by a university without first hiring a significant number of researchers. They can be offered, for example, by a visiting instructor. That's what I do at Northeastern University in Seattle. I'm not like significantly affiliated with them. I'm just a visiting lecturer. But this makes sure that the students who are interested in this topic can have a sneak peek at it early and to figure out whether it is something they want to learn more about, whether this is something they want to do a master's in or a PhD in. Such courses can vary quite a lot depending basically on the preferences of the instructor. They cover the overview of basic concepts, and then they can branch into different directions, such as more advanced algorithms, potential applications, software engineering, implementing those algorithms using current quantum software, or a deeper dive into hardware solutions. There are actually multiple initiatives to develop a cross-university curriculum, again, to enable more universities to offer these courses to their students. One example you see here, NSERC Create quantum computing program that combines, I think, 3 universities. And let me take a couple more minutes to very briefly walk you through one of such courses, Introduction to Quantum Computing in C#, that Microsoft Quantum team actually taught at University of Washington course. It's 2 years ago already. Wow. So this was a course targeting undergraduates of different majors. Yeah, I promised to fit in 5 minutes. Different majors, we had math, computer science, and I think a couple of folks from physics. And it was hosted by Computer Science and Engineering Department, which is quite uncommon for quantum computing courses, which are very often hosted from physics or engineering departments. So in our approach, we focused on making the material as accessible to undergraduate students as humanly possible. So we were kind of realistic about the amount of math and physics background that computer science students have, which is probably insufficient to make them completely comfortable with any topics. So we focused on computer science aspect of things. So we didn't, we eliminated most of the physics from the presentation. We discussed qubits not as particles, but as mathematical abstracts. We eliminated most of the deep proofs of algorithms we discussed. Instead, we focused on implementing those algorithms and encouraging the students to experiment with them, very much like it is done in software engineering, classical software engineering. Here's how we structured our course. We offered the theory in lectures and covered it in written assignments, graded. Those were 20% of the final grade. Then we did a big emphasis on programming, which made up 30% of the final grade in automatically graded programming assignments. So we gave students quantum katas, which is basically programming assignments, programming exercises that gave the students feedback right away for self-study. And then we followed them by programming assignments to actually grade what they have learned. There was also a graded coding competition, which was a favorite of mine, but not so much of the students. And finally, we replaced the final exam on the theory with a final project, which was responsible for 50% of the final grade. And it basically mirrored the experience of a quantum software engineer in the industry in our daily job. So groups of 2 or 3 students chose a topic to work on, an algorithm to implement, a problem to solve, worked on it for 4 weeks, did the implementation, evaluated that implementation, and presented it in the presentations to the class. This course was a great outcome. It had a bunch of great outcomes, actually. At first, several students contributed their projects to open source Quantum Katas project, which I think is great because even if they never do quantum computing again, they already know a lot about open source software contributions. Next, 4 of our 30-something students got internships in quantum computing. Sorry?
Maria, we're going to need to close here. Unfortunately,
This is
already,
the last slide, promise.
We have a couple more, wrap it up about that.
Sure, so you can use this link to read more about this course, and you can contact us to get the materials that we are happy to share with our partners. That's all.
Yes,
and I will be there for the discussion.
Thank you so much, Maria. There's just so much information there. I wish we had an hour for each speaker here. We have 2 very, very quick teasers from 2 corporate speakers. I want to give them 1 minute each before the organizer come with their magic wand. So Eric Holland from Keysight, you want to take the mic minute, and then we'll let Red Pitaya have 1 more minute afterwards.
Yeah, sure. So I'm from Keysight Technologies. I have a PhD in quantum computing. I'm going to give you an overview very similar to what Ron showed. It was funny that we never spoke to each other, but have similar slides and outcomes. So a quick overview of quantum 1.0, 2.0, workforce needs, and then what Keysight's doing in quantum. So next steps and actions. So if you join me, happy to speak with you.